Hi, this is an example problem from chapter 21, and it's about a circular motion of charged particles in a magnetic field, the same principle that we use for mass spectrometers in the chapter as well. Pause for a moment and read the question. All right, so the idea here is that we are accelerating a beam of electrons using this potential difference, and we're going to go ahead and shoot that beam out of here. It's going to come out with its speed, and once it comes out of this region here, it's going to have full speed. It's just going to retain the same speed after that. Once it gets into the magnetic field region, because of the magnetic force, it's going to cause it to go in a circle and eventually be directed into this little cup where you're presumably placing some metal that you want to melt so you can use it as a vapor to deposit on something else. Key thing about the magnetic field, it's only in the region here listed. So it's zero outside of there. And another key idea is because the magnetic force is always perpendicular to the velocity, magnetic forces never speed up or slow down the particles, they just redirect them. And so the speed, the kinetic energy is not affected by the magnetic force. To begin this, we need to figure out that, okay, well, we've got a voltage here, a voltage source. It's 1.2 kilovolts. We know this is the high side, that's the low side, which means that it's on a plate. Think of this as a parallel plate capacitor. There's the low side, there's the high side. Electrons are going to want to accelerate from the low to the high, and when they come out, they're going to have a speed. What's it going to be equal to? Well, to do part A, we're going to have to figure out what is the speed of the electrons. Let's start with conservation of mechanical energy. We assume that there's no air resistance or drag here, so the change in the kinetic energy of the electrons plus the change in the potential energy of the electrons equals 0. Now, Ke final minus Ke initial plus, we're going to replace this with the Q of an electron. So I actually want to make sure that that is, there we go. Keep the sign, we'll need it. Times the voltage equals 0. That's what delta PE is equal to, or delta V, we want to call it that. And in this case, we're going to presume that the electrons are accelerated from rest, right? So the speed here of the electrons, initially, it's 0. When it emerges here, it has sped up to some final speed. What's that? Well, we're going to figure it out right now. So that's 0. And we know this is 1/2 m v final squared. Let's go ahead and subtract this to the other side. So I'm going to minus charge of the electron times the potential difference. We're going to solve for v final. That means multiply by 2 and divide by m, and then take the square root of both sides. Let's put our numbers in here. Minus 2, charge of the electron minus 1.6 times 10 to the minus 19th coulombs. Delta V, 1.2 times 10 to the 3rd volts, or if you want, joules per coulomb, divided by the mass of the electron, 9.11 times 10 to the minus 31st kilograms, and then let's go ahead and do this. This comes out to value of 6.49 times 10 to the 7th, and we should be in meters per second. We notice the negative signs canceled out, which is good. Coulombs canceled out, and finally a joule per kilogram. That is a kilogram meter squared per second squared divided by a kilogram. Cancel out our kilograms, and we're going to square root the meters per second squared, so we do come up with this. Good. Let's look at the next part here. What must be the radius of the beam's circular path so that the electrons enter the center of the cup? Well, that one's going to be pretty straightforward. Here's the semicircle. Here's the radius, but so is this the radius, right? Which, you know, from here to here, it's going to be 1/2 of the 3.7 centimeters. So we can write that value down here. R is equal to 3.70 centimeters divided by 2, which is equal to 1.85 times 10 to the minus second meters. We'll go ahead and convert there. So we got the value there for the radius of the circular motion. And up here, of course, we had the value for the speed of the electrons. And in part C, we're asked, what direction should the magnetic field be in? What direction should it point in, and what must be its magnitude? Well, we'll start with the magnitude first. So in this case, well, if we look at it, right, once the beam is moving, the force is always going to have to point towards the center for the beam so that it stays in a circle. And we know that that type of force is a centripetal force, but we also know that the centripetal force is just a generic term for anything that points towards the center. So in this case, it's going to be the magnetic force that is pointing, because in this region we've got a magnetic field everywhere. And so we've got a force that's going to point towards the center that's produced by the magnetic force. And so in this case, the centripetal force, Fc, its magnitude is going to be equal to the magnetic force, Fb. Centripetal force, Fc, we know that that is equal to mv squared over r from equations that we studied in Physics 2a. And the magnetic force, we know that's going to be equal to the magnitude of the charge times its speed times the magnitude of the magnetic field times sine of the angle between Q and V. Now, so far we've already discovered what the value V is. We've already discovered, let's see, what the value of R is. We know the mass of an electron. We know the charge of an electron. And we can go ahead and use that information to calculate B here. Let's just go back and look real quick. What's the angle going to be? Well, it's going to be 90 degrees. Which means that we can make the magnetic field either come out of the page, point straight up, or point straight down, and that's the way it's going to produce the direction that we want. So, but let's go ahead and calculate this first. So to simplify this equation a little bit, we're going to go ahead and divide by V on both sides. So we'll cancel out this V and one of those, and we're going to put 90 degrees in here so that this whole thing is equal to 1. And we're going to come up with an equation that tells us how charges will move in circles for the special circumstance where the velocity and the magnetic field vectors are perpendicular or 90 degrees to one another. So we end up with an equation that looks like this. mv over r is equal to Q times B. And as we said before, we know a bunch of stuff here. We know this, we know this, we know this, we know this. In this case, it's going to be B that we solve for. So to do a little bit of algebra, B is going to be equal to mv divided by qr. And the mass of the electron, 9.11 times 10 to the minus 31st kilograms. The speed from part A, 6.49 times 10 to the 7th meters per second. The charge of the electron, absolute value in this case, we're dealing with magnitudes, 1.6 times 10 to the minus 19th coulombs. And finally the radius, which we determined in part B, 1.85 times 10 to the minus second meters. Plug it in the numbers, this comes out to 2.00 times 10 to the minus second Tesla. And now I know we're going to be in Tesla simply because I've been in SI units everywhere, so we want to just remember that. All right, we're almost done with this problem. The only thing we have left here is, what should the direction of the magnetic field be? Well, to figure that out, we know that the instant that the charge first shows up here into the magnetic field region, right here, that's the direction of its velocity. So we know that. And we also need to figure out that we also know that the force direction needs to be in this direction, right? Okay. But these are electrons, right? So we're going to go ahead and use the right-hand rule to see what direction B should be. And we're going to remember that the actual force for the electrons would be opposite what the right-hand rule number 1 tells us. So let's bring in the right-hand rule and just check this. So here's a picture of our right-hand rule number 1. And let's go ahead and put our charge here. We're going to go ahead and line this thing up right here. So V goes in the direction up. And notice I take my magnetic field, that's the fingers, they point straight out of the page here, right? Oops. So overlaying our right hand, the fingers pointing straight up out of the screen, or out of the page, the charge moving straight forward as it first enters the, straight upwards as it first enters the magnetic field region. For a positive charge, it would point in this direction, right? But this is an electron, so we don't go in that direction. We, in fact, go in the other direction. And this does work out. Yes, perfect. So if we have the magnetic field pointing straight out of the page, we're going to get the curvature that we want for the electron to be redirected through a circular path right into that cup. Now, let me go ahead and just remove this for a second. And how do we indicate that the magnetic field is pointed out of the page? Well, we draw little dots, and the little dots represent tips of the magnetic field vectors, and they indicate that the magnetic field is directed out of the page. And so that pretty much wraps us up for this problem. You've got a similar one in your homework, or a couple of them that have to do with mass spectrometry, and this is the same idea. So just to finish this one up, a magnetic field has a magnitude there, and it's pointed out of page.